Okay, this is going to be the introduction to circles and ellipses. Briefly talking about circles. Every circle has a general equation, and I just want to show you how that general equation is derived. The first thing is that we just choose some center of our circle, HK, and then any point that is on our circle. So what's going to happen here is that we're going to have a formula that regardless of these points, that one and that one, we should be able to plug into and we'll get a true statement. So that means every point on this circle should satisfy this general equation we'll come up with here in a moment. But as I draw from the center to x, y, any line that I draw in the coordinate plane, as long as it's not vertical or horizontal, and those are special cases that are really easy to decipher anyways, the segment drawn is always the hypotenuse of some right triangle. So we've got that leg right there and that leg right there of a right triangle. And that's true in every single circle. That point right there, based on being on a vertical line with x, y, is going to have an x coordinate of x, and on the horizontal line with hk, will have a y coordinate of k. And now the idea is if that any values of x, k, h, and y that satisfy the condition of that's set forth in the right triangle in regards to distances, a squared plus b squared equals c squared, should generate then an equation for a circle. So I'll find that red distance, and because it's horizontal, all I got to do is take x minus h. And I'll find that blue distance, because it's vertical, all I've got to do is take y minus k. And we then say that this distance here, which usually we call c, but I'm going to relabel it as r, standing in for radius, we should be able to say then that because of a squared plus b squared is equal to c squared, then I should be able to say a, which is one of my legs, x minus h squared, plus then b, which is my other leg, y minus k squared, should equal my radius squared as well. And that turns out to be the equation for any circle with center located at h, comma, k. The only thing to pay attention to here is because x and y are on the same side of the equation when we do transformations. Like say, let's go, I had like x minus 3 squared plus y plus 2 squared is equal to 9. So r squared is 9, so r squared is equal to 9. So r would be 3, so my radius is 3. And my center is going to be located, generally speaking, the most simplistic position for our center obviously is 0, 0. But if I subtract 3 from it, it's going to actually move it to the right 3 units. Okay, and that's the same as what we've always talked about with transformations. But now because y is on the same side as x, when I add 2 to y, instead of moving up 2, I'm actually going to move it down 2. So we'll have a center of my circle is going to be located at 3, comma, negative 2. That's really the only thing you have to pay attention to when you're graphing circles and dealing with them. The reason I want to talk about this is how that relates then eventually to ellipses. Okay, so we'll come back to this a little bit after we talk about ellipses. By definition, an ellipse is the set of all points in which the sum of the distances from a focus to the ellipse plus then from that point on the ellipse to the other focus, that sum is always constant, a fixed number, meaning that these black segments added together should equal the same as these blue ones added together, which should equal the same as these red ones, added together, and then any other ones that we could draw in there. That distance is always going to be the same. The kind of GeoGebra concept here would be if we were to take let's just take a circle of some size, and this is just to kind of generate the size of a ellipse that I'm looking for. So it doesn't, the circle that I'm going to create here in a moment really doesn't matter a whole lot. So I have my focus number 1, and let's say this is focus number 2. All right, and I'm going to center, so it doesn't matter which one of these we do this with, focus 1 or focus 2. I'm going to center a circle around focus 1 with a radius equal to AB. All right, so that AB is just going to basically dictate the size of my ellipse here in a little bit. So I just put a point on the circle, okay? And now this process I'm going to go through is just to generate distances that are always going to be summed to be the same value, meaning if I take that distance right there, that is now my constant that I'm going to try to get my two foci lengths to add up to. And when I say foci, I don't even know if that's a term to use, but what I'm talking about is this black distance plus that black distance needs to be constant with that blue distance plus that blue distance. So I need a constant value to reference those two to get them to add up to, and that's going to be this distance here. I'm then going to, so some of the stuff that you see me doing here might not make a whole lot of sense right off the bat, but I'm going to create that segment, and I'm going to find the perpendicular bisector of that segment, which would be that one. And there should be a point then of intersection, the perpendicular bisector and the radius of that original circle. And what I've just done here, if I connect D to F2, if we look at just this triangle right there, what I've done is I have forced this thing to be isosceles, because there's a theorem that says that if you take a base of your isosceles triangle and you find the perpendicular bisector of it, that's going to go through the vertex angle. So basically I was trying to find that vertex angle so that I can create this isosceles triangle. Why do I need that isosceles triangle? Let's think about this. These two segments between F2 and D, and then DC, those two segments are the legs in an isosceles triangle. So let me get that other one in here to be blue as well. Okay, those are the legs of an isosceles triangle. Okay, and as I move C, so what I'm done here is those are always going to be the legs of my isosceles triangle. So I have to find the distance of them. Well, I think it just gave me perimeter. Distance from D to C and distance from D to F2. As you see that they're the same, let me do that. And they're always going to be the same. So that's always an isosceles triangle there. Okay. So why do I have to do that? Because if I think about this distance, okay, if I think about that red distance, that is now F1 to D, so that distance there, plus this blue distance, okay, that's my radius, that's my constant, okay. That is always going to be equal to this red distance plus that blue distance. So what I've got going on here is a way to, no matter what I deal with, no matter where that point C is, this red distance plus that blue distance is always constant. It's always the same thing as this radius. So if I were to do this, let's hide some stuff here. Let's hide the circle. Let's hide this triangle and the parts that make it. Hide that line, hide that line, and what we've got now is focus 1, focus 2, and this point D, and I've forced that no matter where I move that point D, no matter where I move point D, the sum of, let's go F1 to D, that distance, let's see how I can find that. We've got to do it this way. That distance and that distance, move them apart from one another. If I were to add those together, so let's go, they're calling it N plus L, okay, which ends up being that number right there. So that number right there, that 5.564, is what I would get if I add those two numbers together, F1 to D and F2 to D. And as I move D, okay, those numbers change respectively, but look at their sums, still 5.564. All the way around there, it's the same. So what am I getting here? I'm forcing these two sums to be the same. So if I were to trace point D, we should trace out our ellipse. Okay, so that's our definition of ellipse, is that those two, that red distance and that blue distance, should be the same. Their sum should be the same all the time. Now, using that to do some specific problems or concepts is going to be useful, but we need a formula. We need a formula for writing the equation of ellipse. And basically, in regards to coming up with the formula for an ellipse, we need to know what should that sum always be. So we could take a general ellipse. We call this the minor axis because it's the smallest one. We call that the major axis because it's the larger axis, and that can be switched. One could be, the major axis could be the vertical one, and the minor could be the horizontal one. We've got these points here. That's my focus 1. This is my focus 2. We just let those be arbitrary values, negative C, positive C, and they're on the axes. They're on the major axes. These are referred to as vertices. Okay, negative A, comma 0, and A, comma 0. Those are vertices. And we can call these kind of minor axes vertices, or the endpoints of the minor axes. But every parabola is going to, or sorry, every ellipse is going to have that information. Okay, but what we do is we center it at 0, 0, so I come up with an equation. Now, the idea is I need to be able to state what the distance from F1 to my ellipse, so let's just call that point P, to F2. I should be able to know the sum of that, those two black lines. Well, there's a really convenient place to do this, and it's to put P right there at negative A, comma 0, because then we're able to find F1 to P. So F1 to P would just be that distance right there. Well, that's horizontal, and to find the horizontal distance, we just take the x-coordinates of negative C and negative A, and we subtract them. So we get negative C plus A as that red distance. Then what we're going to do, so that's from focus 1 to point P. I want to find the distance from focus 2 to point P. All right. Now, I'm not going to take C. Well, I can, I guess. C minus negative A, because that's that x-coordinate, minus that x-coordinate to find that distance. So that becomes C plus A. So then if I got the red distance plus the blue distance, if I add those two things together, negative C plus C, well, those cancel out. I got A plus A, so I get 2A. So to that point right there, to focus 1, and that point to focus 2, that sum is 2A. So what that means to me is that no matter where that point P goes, if P is there, that sum of that distance and that distance still has to be 2A. So that's nice. So we got a total. The next thing we do, so we know that the sum should be 2A. The next thing we do is we just put a point P anywhere on here, x comma y, and we're going to find what that arbitrary distance is. So we use the distance formula. So we're going to say the distance for F1 to P, so F1 to P should be, it'd be x minus negative C, so it becomes x plus C squared, and then y minus 0 squared. So that's just the distance formula, x2 minus x1 squared plus y2 minus y1 squared. And then we'll do the same thing for distance from F2 to P. So here's F2. So I go x minus C squared plus y minus 0 squared. So those are the two distances, F1P and F2P. Remember, we're going to add those together, and we should get 2A. So what we're going to do is we're going to write this as x plus C squared plus y squared plus x minus C squared plus y squared should equal 2A. And now all we're going to do is we're going to try to manipulate this to get an equation that is useful. that's friendly. So the first thing I'm going to do is I'm going to try to isolate one of these radicals. So I'm just going to isolate this first one. So I have x plus c squared plus y squared is equal to 2a minus x minus c squared plus y squared. Now we can square both sides. This is going to start to get ugly here pretty quickly. If I square both sides, it gives me x plus c squared plus y squared. On the right-hand side, now I got a FOIL, so I'll get 4a squared minus 4a. Now it'd be x minus c squared plus y squared. And then plus last times last would give me x minus c squared plus y squared. Okay, so now I'm just going to try to isolate the 4a transferring a square again and get rid of that radical. So I'm just going to move it over here so it becomes positive. X minus c squared plus y squared underneath there. I'm going to move this stuff to the other side, so I'd have a 4a squared. It'll be then plus x minus c squared plus y squared minus then x plus c squared minus y squared. The nice thing here is that the y squareds cancel. And then I'm going to, before I address this, let's just kind of clean the right-hand side up. We have 4a squared. It's going to be plus x squared minus 2xc plus c squared minus then this is going to be x squared. It'd be plus 2xc, but it's minus that, so minus 2xc. And then it would be plus c squared, but it's going to be a minus, so minus c squared. And then there's some other cancellations occur. Those cancel. My x squareds cancel. And I'm going to have, 4a squared minus 4xc is equal to now 4a x minus c squared plus y squared. Another radical. I should be able to take a 4 out of everything, so let's do that. Let's wipe those 4s out. That's going to be nice. And let's bring this up here, get rid of that. Let's bring this statement where we've got a, and then x minus c squared plus y squared is equal to a squared minus xc. Alright, so now we can square. Square the left-hand side, so it's going to be a squared times quantity x minus c squared plus y squared. And then if I square the right-hand side, squaring this, I'm going to have to FOIL that again, so it would be a to the 4th minus then multiply those two things together and double would be 2a squared xc's. And then last times last would be plus x squared c squared. Alright, it's kind of ugly. I should probably address this x minus c squared, so let's expand that. X squared minus 2xc plus c squared plus then my y squared is now equal a to the 4th minus 2a squared xc plus x squared c squared. Okay, now we're just going to rearrange terms. I'm going to distribute that a squared through. A squared x squared minus 2 a squared xc plus a squared c squared plus a squared y squared is equal to a to the 4th minus 2a squared xc plus x squared c squared. Now it's going to get kind of messy, but my goal here is I'm actually going to move that to the other side, and then I'm going to move that to the other side. You're going to see the purpose of that here in a moment. So I'll have a squared x squared minus 2a squared xc minus x squared c squared plus a squared y squared is equal to a to the 4th minus 2a squared xc minus, then I'm moving this thing to the other side, so it'd be minus a squared y squared. Now, why you do that? Well, first thing to notice is that that term right there and that term right there should wipe away. So I'm left with a squared x squared minus x squared c squared plus a squared y squared. Now I apologize, I wasn't moving that over. I moved that over. So that should be a c right there. A squared c squared, not a squared y squared. So now this is equal to a to the fourth minus a squared c squared. Now we're going to look at these first two terms on the left-hand side, and they have an x squared in them. So I'm going to factor that x squared out. So it's going to be a squared minus c squared, and then it's going to be a squared y squared. Now if I look at these two, they have an a squared in them, so I'll take that out, and I'm left with a squared minus c squared. Well, that a squared minus c squared, that thing in the parentheses is on both sides. So what I'm going to do, and we can do this, I'm going to rename that. I'm going to call that b squared. I'll call that b squared. It just makes things, the substitution here, convenient. So now I make the algebra convenient. I have x squared b squared plus a squared y squared is equal to a squared b squared. Well, in every one of our ellipses and a formula that we're interested in, we want this right-hand side to be 1. So what we'll do is we'll divide by a squared b squared. Come over here, divide by a squared b squared b squared, and now some cancellation occurs. The b squareds cancel out. So it gives me x squared over a squared plus then, now here the a squareds cancel out. So I have y squared over b squared is equal to 1. And the idea then is that is when b squared is equal to a squared minus c squared. And if I just do a little bit of manipulation here, add the c squared to both sides and subtract b squared from both sides, we actually get that c squared is equal to a squared minus b squared. But this is the general equation for any ellipse. I know that's messy, it was time consuming, but I want you to see that there is reason for these formulas. Now just some general procedure here. I don't remember any of this stuff, especially this here and there. I just look at the comparison of these numbers. Whichever number, a squared or b squared, that is largest is going to provide the major axes. And then if the a squared was larger and it's paired with the x squared, then the major axis is on the x-axis. If this number was larger, then your major axis would be with your y. Your vertices are always at the square root of that largest denominator. All right, and then your minor axes endpoints are going to be at the square root of that smaller value. Your foci is always found by using that c squared equals a squared minus b squared approach. So all you got to do, we remember when we take we're looking for a distance, so we want a positive number, so we just take the larger of these two, subtract then the smaller of these two, and then take square root, and that gives us our c value. So I'm going to do an example here and kind of walk through how we distinguish this. It says an ellipse has this equation: find the foci, the vertices, the length of major and minor axes. Okay, so that number is bigger. That number then is paired with x. So right now I know my x-axis is going to be my major axis. Okay. So now my major, so I take the square root of that number, it gives me 3. So my major axis is going to have endpoints at 3 and negative 3. This number here, I take square root of that, that's going to be my minor axis, so it's 2 and negative 2. So 3, 0, 0, 2, 0, negative 2, and this would be negative 3, 0. And now my foci is going to be, c squared is equal to a squared minus b squared. So c squared is equal to, now a squared minus b squared, that's, I want a positive number here. So I'm going to go 9 minus 4. So it gives me c squared is equal to 5. So c is plus or minus root 5. So my foci, whatever plus or minus root 5 is, a little bit bigger than 2. So it'd be root 5, comma 0, and over here we would have negative root 5, comma 0. And all we do then is just connect the major and minor axes, vertices, or endpoints, and there's our ellipse. One thing I think you guys should remember is the, if I do a squared minus b squared, if I did that backwards, I have c squared is equal to 4 minus 9. Well, I can't take the square root of negative 5. So that's why I knew it was 9 minus 4. So it's the biggest number minus the smallest number. If we think about it, this is the exact same formula. If I take x squared plus y squared is equal to r squared, that's the formula for a circle. Okay. Well, if I were to divide everything by r squared, x squared over r squared plus y squared over r squared is equal to 1. This is very similar to the equation of an ellipse. In an ellipse, in a circle, the major axes and minor axes are the same thing. So the r squared would be the same number. So if I had like x squared plus y squared is equal to 36, I'd have x squared over 36 plus y squared over 36 is equal to 1. But with an ellipse, this number here might actually be, let's say, a 9, and let's say this one's a 4. So then when I go 9 and a 4 there, so 9 divided by 36 would put a 4 in the bottom, and then 4 divided by 36 would be a 9 there. So what that does is that's a circle very similar to x squared plus y squared equals 36, but now it's elongated in the y direction a little bit more than what the circle would have been. So that's the relationship that I always use to remind myself of which one's the ellipse and which one's the hyperbola, because the hyperbola is going to be very similar, but that sign's going to be negative. So I remember, well, an ellipse and a circle are very similar, and a circle is x squared plus y squared. So an ellipse is going to be x squared plus y squared. When they ask you to do something like this, again, this has got to be a 1. So we've got to divide by 144, 144, 144. So what happens is that's going to turn into 16 divided by 144 is 1/9. So you get x squared over 9. 144 divided by 9 gives me 16, so that's going to be y squared over 16 is equal to 1. So now, when I graph that ellipse, this number is larger than that one. So I take the square root of that one, gives me 4. So my y-axis is going to be the major axis, 1, 2, 3, 4. So 0, 4 is that endpoint. 1, 2, 3, 4. 0, negative 4 would be that one. Square root of this one, so it'd be 3. So negative 3, 0. This one's going to be out here, it'd be 3, 0. My foci is found by taking those two numbers in their correct order, subtracting them. It's going to give me 7. So remember, c squared is equal to that, so c is equal to root 7. So root 7, wherever that ends up being, would be, your foci are always on your major axes. Now, this ellipse is pretty ugly looking, but my foci are going to be whatever root 7 equates to as a decimal. Find that, and those would be the locations then, plus or minus root 7, comma 0 for those foci. So this isn't too bad, I don't think, for ellipses, finding those pieces of information and then graphing the accompanying picture. Here they tell you just really the same stuff. It says the vertices of an ellipse are at negative 4, positive 4, comma 0. So right now, if I go out to 4, 0, and negative 4, 0, what that does for me, it tells me, my ellipse is going to be an x squared over some number squared plus y squared over some number squared is equal to 1. Well, these numbers here come from knowing where my ellipse had a major axis, and it's at, remember, this is a, comma 0, and this is negative a, comma 0. But a was found by just taking the square root of this number. Well, if I take the square root of a number and got 4, that number had to be 16. And I know to put that under x because x is my major axis. If my major axis was, maybe at this point was 0 and negative 4, then that would be my major axis on the y. So then I would put that 16 under here. Okay. The foci are at 2, negative 2. Well, that's going to tell me what this number here is, because I need a b squared. Well, remember, c squared is equal to a squared minus b squared. So the foci, that plus or minus 2, is coming from, that's c, so this would be 4. Now, a squared minus c squared, well, a has got to be my biggest number, so 16 minus b squared. So now I'll subtract 16, so I get negative 12 is equal to negative b squared. So b squared is equal to 12, so b is going to be, or sorry, b squared is 12. Now, don't go any further with that because that's what goes here. It's a squared number. So 12 goes there. And if I just kind of type this stuff in real quick to GeoGebra, if I type in, what do we have, x squared over 16 plus then y squared over 12, that equals 1, gives me that ellipse. You see my endpoints are at negative 4, 4. Let's see if it finds the foci for me, if I can do that. It won't, I don't think. No, but I can do this. I can go 2, 0, negative 2, 0, and we can check these distances, I think, this way, just to make sure that those are that is the right ellipse. We should be able to take that to that. If those foci are true, then CB, which is F, plus CA, which is G, should always be the same. So it's saying 8, no matter where C goes. And you see that number 8 is not changing no matter where C goes. So that's kind of the approach there. They're going to give you information that allows you somehow to fill in this x squared over a squared plus y squared over b squared equals 1, somehow finding a and b through the use of probably that formula, c squared equals a squared minus b squared, where c is the location of your foci, plus or minus. I think that should be enough for you guys to kind of maybe fight through that explanation of ellipses and those accompanying assignments that go with it. Hopefully that helps. Let me know if you have any questions.